machine learning. And I have to announce that we have some minor changes in the program. Unfortunately, some of the authors have no opportunity to come here today. But we have young and dynamic people that actually stepped in and will give presentations instead of them, or instead of one at least. So you're into some surprises in this session, but we start with the first speaker as announced in the program, Ms. Goutami does, with a paper on the machine learning-based prediction of pore pressure and geophysical laws. Please.
Please welcome the author with a round of applause. And respected delegates, I am Goutami, currently pursuing PhD in the Department of Applied Geophysics of IIT ISM Dhanbad under Professor Shobin. And here is my topic, a machine learning based prediction of pore pressure from geophysical log of Hinkurangi, Tuaheni zone. This is my presentation outline, which covers the title, introduction, objective, methods, results, and conclusions. So, I will tell you why pore pressure prediction is important. Pore pressure is the pressure in the fluid of the rock spaces, and pore pressure, accurate estimation of pore pressure is needed, otherwise it can lead to the well blowout. So, to increase the wellbore stability and to increase the wellbore stability, accurate prediction of the pore pressure is needed, and it also helps in selecting casing points when the well log is planted. So there are various empirical methods are available which can be used for the pore pressure prediction by the use of geophysical well logging data. I have used the Eaton's empirical transformation method for the predicting of pore pressure. Now, what we have seen that in the theoretical approach, there is the most of the theoretical framework is deterministic. That if you give the various outputs, at some point it will give the same output. To overcome this constraint, I have implemented the machine learning technique, which is the random forest regression method. And what is random forest regression? Random forest regression is an ensemble learning technique which takes multiple trees and combines them. Here you can see in this figure that there are various bags are there. From the whole data set, 2/3 data are taken randomly in one bag. It is optimized, and the rest of the 1/3 data go to the out of bag samples method, and this is go consequently. And this is the random forest method. Why I have chosen? Because there is the less need of data preparation, and it gives the accurate result, and the error is most of the time is minimal. So these are the reasons that I have chosen random forest technique. And this is my in figure 2 I have showcased the gamma ray density, porosity, and sonic velocity of my well log data. This is the study area. So my study area I have chosen the landslide complex of northern Hinkurangi subduction zone, which is situated in New Zealand, and the well was U1517A, and the data was collected during IDP expedition 372. And the well log data, which was acquired at the depth of 725 meters below sea level during the IDP expedition, and the well site consists of massive clayish silt to silty clay. There are the clay lithology was there. So this is my workflow. First, I have started with the theoretical framework using Eaton's method, and then it was giving the theoretical framework for my machine learning technique, where I have taken 7 parameters that are the sonic travel time, bar density, gamma ray, caliper, temperature, neutron porosity, and NMR porosity. So first I have collected all the data, and then it was sorted, establishing maximum and minimum value variables. It was scaled between -1 to +1 range, and then the statistical analysis was performed using the Pearson correlation matrix, which is step 4. And coming to step 5, the data was divided into two parts. This is the main part where I have divided the data into part where 70% data was used for training and the 30% data was used for testing. Now the total model accuracy was calculated or measured through 4 matrices, which are the MSC, mean square error, RMSC, root mean square error, R square, the correlation coefficient, and the mean absolute error. So this is the normal compaction trend time from sonic travel time versus depth plot. Actually, this plot was done for the PP prediction using Eaton's method. That optimum fitted line, which is called the normal compaction trend line, and the slope was giving the value for the prediction of pore pressure from Eaton's method. And then the machine learning technique was performed. The statistical analysis was done using this Pearson correlation coefficient, where the blue is showing the stronger correlation, maybe the TT is the sonic travel time, and a total 8,491 data records were compiled for this for performing this technique. And now I have this work was conducted in scikit-learn with a Python environment, and these are the hyperparameter which was tuned for that optimum performance of the model, and the number of estimated methods where what we have there is 1,000, and the maximum depth was also 1,000. Now these are the result, and first figure is showing the regression result where predicted and the observed value. The correlation is showing with the R square value 0.79, almost 75% it was correlated, where the only well-loving parameters were used to predict the pore pressure. And coming to the next picture, where the past pore pressure was used to predict the future prediction. Here both the well-log data and the pore pressure was in the input, and the output was future prediction. It was one-log prediction. Now this table is measuring the training and testing data set model accuracy. The first RFR one is where the well-logs are used as a only input parameter, where R square for training is very good, 0.97, 97%, and for the testing it was 0.74 above the average. And for the RFR2, where I have taken the pore pressure as input and output, I also get the one-log prediction. Here the training was almost 0.99%, and in the testing dataset it was also 0.99%, which is a good correlation. Now coming to the conclusions, that we can tell that RFR can be handy tool to achieve the reasonable accuracy with limited data exposure. Now my technique predicts the anomalous pore pressure at the depth of 870 meter below sea level at the well of U1517, and this was the indication of the patchy BSR potential-emitting reflector in that area. And the present analysis would provide insight into the geomechanical activities in the Hinkurangi subduction zone. Actually, the pore pressure prediction was not conducted in that zone of Hinkurangi subduction. It will provide some insight into that area, and the trade. I have trained that RFR model. It can be used in other area also if the same lithological or geological information is available for that area. So these are my references, and thank you.
I invite the next speaker. You invite?
I invite.
Oh.
Good morning, everyone. I am Ashmita De. I am currently pursuing my MTech degree from IIT Guwahati under the guidance of Dr. Arindam De, Associate Professor, IIT Guwahati. So today, first of all, I would like to express my gratitude to all of you for giving me a chance to present. So today I am going to present a review on underwater MASW with respect to source and wave characteristics. So this is the contents that I will go through briefly. So first, to introduce multi-channel analysis of surface waves. As we all know, it is a technique which is used for subsurface investigation. investigation for determination of underground sediment deposit layers and all. So here we are, if this same technique, instead of using on land, if we are using it under the water, then it is called underwater MSW or UMSW. So it is mainly used for the investigation of offshore sediments and underwater surface conditions. So in offshore surveys, it comprises of the following type of measurements like the bathymetric data for defining the seabed morphology, side scan sonar for the seabed features, and the seismic refraction data for soil layering. And due to the various advantages provided by the MSW technique for the marine sediments, it is in increased demand nowadays, and still a very less explored area. So this is the points are like the increased precision for the positioning of the reflectors at depth, the characterizing of the nature and stiffness of the subsoil underwater, and to correlate the geophysical data with the geotechnical data. So based on the survey results obtained from different experiments, these are classified, the underwater exploration are classified into these three categories based on the maps of the physical values, cross-section of the interfaces, and the spatial distribution of the physical values. So the first category, these three techniques comes: magnetic, electromagnetic, and self-potential method. And in this, which gives the point-by-point measurements, confirm location of the target objects, but it gives only the rough estimate of the volume and depth of target object. And the second section, the side scan sonar, multi or single beam sonar, and sub-bottom profiler, etc. are used, ground penetrating radar, and these are only giving the physical quantity changes. As we can see, there is a distinction between the surface is observed in the results. But in the third one, where seismic refraction, seismic surface wave, electrical resistive tomography, and induced polarization methods are used, here inversion technology is used, and here we can obtain the physical values of the quantities, and the exact value of the depth of the target object can also be obtained. And there is another classification based on the quantitative and the qualitative results that are obtained, as we can see. So MSW will come under the underwater seismic surface wave method here, and these are the different results that are obtained, different subsurface profiles using the different techniques. Then comes where these are used, like the application of the UMSW. So it has various applications like geotechnical investigations for shallow anchor systems, profiling of underwater pipelines and cable routes, and also the measurement of in situ small strain shear stress, shear modulus, hydrocarbon infrastructures, and in detecting the gas hydrates. And it is very much useful in the oil industries also. So next comes the development. So first it was it is derived from the Gambus tool, which was used for the high resolution seismic refraction system by Kurukshetra in 2004, where a seismic refraction experiment was done. And as we can see in this figure, a sledge is pulled along the sea floor, and there is a source and the hydrophone streamers and the data processing unit, and an umbilical cord is connected with the source and the streamer. So it was a seismic refraction method, and later it was developed into seismic surface wave method with some changes. So next there was a question like how these instruments are installed under the water. So here first a streamer is on the water, then there is a primary weight that is put down on the seabed. Then as the streamer is pulled along the sea the hydrophones are being laid with the help of the weight. And then here the Long et al. 2020 is a paper from there where they were used 24 geophones and 48 geophones arrays. Then this how it is instrumented in the sea. Then the source type here in any MSW survey, source is the main important factor. So here the source is different as on land. Here we use they have used air gun, shotgun or weight drop, and mini G gun, sleeve gun. There are different type of air guns that are used, but the limitation is that air gun can requires highly efficient air compressor, and it can't be used for shallow waters and intertidal regions. But shotgun can be used due to the heavy weight in the shallow water in the up to less than 10 meters. And in another experiment in Kurukshetra paper, they have used mini G gun and sleeve gun to determine the energy content generated by the source at different water column depths with respect to different frequencies. So it was observed that as the depth of the water goes on, water column goes on increasing, then the energy content generated by the source goes on decreasing with the depth and also with the frequency. So this is a field where more research is required related to more development of the source of this UMSW. Next, the waves that are generated in this UMSW are also known as Scholte waves, which are a type of three different type of waves that are obtained from the solution of the equation. So the first mode equation gives the gravity-driven wave, which is also called the guided wave, as we can see in this figure, which are the waves traveling along the water column. And then the second mode solution gives the Scholte waves, which are the waves along the interface of the water and the soil beneath water. And the third mode solution gives the acoustic waves in the water and the surface, also similar to surface waves in solid. And another classification of the waves is also based on the shear wave velocity compared with the velocity of compressive waves in water. So when the Vs is less than Vw, it is called Scholte waves, which indicates the soft substrate beneath the water. And when it is vice versa, Vs is greater than Vw, it is for generalized Rayleigh waves, and it indicates the stiff substrate. It is also classified based on the ratio between wavelength of the wave in water corresponding to the depth of water. Then comes the physics of Scholte waves, or like how it is different from Rayleigh-wave. So Scholte in 1947 gave this equation for the viscoelastic medium, also for the motion of the particle in an infinite body, but this equation does not have any boundary conditions. So any type of motion comes under this. And here lambda and mu are given by these equations, where lambda 1, mu 1 are the length constant, and lambda 2 and mu 2 are the viscoelastic constant. And this is the famous Rayleigh equation for the semi-infinite body, where there is
2 minutes.
There are 3 solutions which are complex, so it gives periodical motion in Z and exponential motion in X, and by getting different solutions, it was observed that the Poisson's ratio and viscosity affects the motion of the particle in the X and Z direction, and which makes the difference between Scholte and Rayleigh wave on length. Then there are some case studies that I would like to go through. First, it is by Park et al. In 2005, where they took 3 sites in the they got these raw data. Then after then they got the comparison between the Scholte wave and the Rayleigh-wave, which is nearly 5% from this inversion curve. Then and here also in the dispersion image we can see that the frequency range nearly between 0 to 20. The Scholte waves are coming for fundamental, first and higher orders. Then in the second, it is that canvas experiment, second case study. Here also we can see the Scholte wave in this dispersion curve, inversion, and the comparison between Rayleigh and Scholte waves. And the third case study, it was done in the Manifa Causeway, Saudi Arabia, for characterizing the Cape Rock in the underwater regions, and they did the data acquisition and analysis using the surface software, and they observed the Cape Rock, sand and soft sediments, and this is the S-wave velocity profile that is observed. And after that, these three different distributions of seabed hardness, Cape Rock distribution, and sand and clay distribution was observed. And from this review, I found that these are the challenges and the future developments, like shortcomings in the operational efficiency, lack of appropriate application equipments and systems, and the insufficient guidance for the nearshore application. And these are the references. Thank you.
Thank you very much. Rayleigh-wave multimode phase velocity dispersion curves using CNN. So we're back to machine learning.
So very good afternoon to one and all present here. And today I will be presenting on the joint inversion of Rayleigh-wave multimode phase velocity dispersion curves using convolution neural networks. So these are so I'll start by introducing the authors. So first up, my name is Rohan Sharma and I'm an undergraduate student from the Department of Applied Geophysics from IIT ISM Dhanbad. My first co-author is Divakar Vashisht, who is a PhD student at Stanford University under Professor Tapan Mukherjee. And my second co-author is Professor Bharat Shekhar from the Department of Earth Sciences at IIT Bombay. Okay, so I want to start off by introducing the topic of surface wave dispersion curves. So it has a lot of applications in near surface studies. And here are some to list. So we have groundwater assessment, delineating fault zones, environmental geophysics. I've also read literature where archaeologists make use of surface wave dispersion curves. And you can also use it for assessment of soil liquefaction potential and passive seismic studies. So since this has a lot of applications, I thought that my first part of research should be in this domain. So I would start off by introducing the inverse problem first. So in the forward modeling, we have the S-wave velocity profile, and along with the P-wave velocity profile and densities, we could generate the dispersion curves. To generate these, we used Herman's codes, which is written in a Python package called SRF Python. It is a Python 2.7 package, and it is available like open source. And the inverse problem now is quite complicated. It is because it is inherently ill-posed, non-linear, non-unique, and mixed determined. So we needed some really good algorithm to solve this, and why we went for joint inversion has two main reasons for it. And the two main reasons for it were that it aids in the identification of high velocity and low velocity layers. And how does this happen is basically that certain frequency bands display certain energy levels when there is presence of higher and lower velocity layers present in the substrata. So that is one of the reasons, but the key reason, however, is to have a better investigation with respect to depth. So what basically happens is that certain frequencies at the higher higher modes have higher phase velocities and therefore higher penetration depth. So this is why incorporating the higher modes would be beneficial in helping us delineate the deeper strata. With that, I would like to address the question of why deep learning. So, a lot of literature actually makes use of local optimization techniques. But local optimization techniques suffer from something called local convergence. So, in this, what happens is that the solution is highly biased to what initial solution you choose to use. And when there are also literature pertaining to the use of global optimization, but it comes with the disadvantage of rerunning the algorithm over and over again with the incorporating of new data points. So deep learning certainly surpasses these issues, and we currently live in the deep learning era. I would like to add another perspective that with the rise of AI, we want to minimize the human intervention part, and I believe that this work that I have done here is a first step to that, since we have attempted to keep our model agnostic to the number of layers that has to be defined to, from a prior geologic source for the optimization to work properly. And we also obtain better fits in the process, and deep learning algorithms can be easily fine-tuned based on the local geological information. So the requirement to any deep learning algorithm is sufficient data and an architecture that is complex enough to capture the underlying relationship between the inputs and outputs, which here are the S-wave velocity profiles and the dispersion curves. So this is DispersioNET. This is an architecture that I came up with. This came after a rigorous search over a lot of architectures. And this found out to be the optimal one in terms of having lesser number of architectures, lesser number of parameters, as well as giving the best fit. So the architecture basically consists of 3x1 convolutions at the start. The 3 in the 3x1 corresponds to the 3 channels, which are each phases. They had 16 points each and corresponding to a certain set of frequencies. And we didn't have to feed the frequencies as input. This is another thing that I would like to know. And then the following filters were all of 3x7, and there were like 4 other layers for it. It was followed by a dense layer with 275 nodes. I would like to elaborate on this shortly. And this was then giving the output. So Rayleigh activation was used, and we used this whole architecture was optimized on the mean squared error as the loss function between the predicted and the observed S-wave velocity profiles. So the number of parameters are like less than 400,000, and this can be easily trained in a GPU setting. With that, I would like to now come to the dataset generation, which is another crucial part of deep learning algorithms. So deep learning are quite data hungry, and a good amount of data points were therefore necessary. So this is the search space that we used for our dataset generation process. This was derived from Vashisht et al. 2022. They used a similar search space, and we followed it here as well. The innovation here, again, as I mentioned earlier, is that we discretized the number of layers. So we basically went to a resolution of 0.1 meters, and our depth of investigation because of this search space was around like 27.5 meters. So therefore, we had 275 layers in the output node. So having this discretization therefore enables us to forego the process of giving a prior information about the number of layers in the underlying strata. So, while generating the dispersion curves, the densities and P-wave velocities were accordingly linearly scaled with respect to the S-wave velocity profiles, and 30,000 profiles were generated, and they were sampled from this search space, and they were fed into the Hema scores, and the corresponding dispersion curves were generated. 70% of the total samples were used for training, and the rest for testing. So We also, to simulate the field results, it was important for us to add a fair bit of noise. So we created another data set with the help of the original one by simply adding a frequency dependent noise. Since the higher frequency content doesn't have a lot of penetration depth, we added we linearly varied the amount of noise from 5 to 10% ranging from the higher to lower frequencies. So, and here are the results. So on the noise-free dispersion curves, the convolution neural network model that we proposed, DispersioNET, could capture a lot of the physics. And these are the fits that we obtained. So you can see that the train set fits are like pretty perfect, and the test set fits denote the significance that how well can DispersioNET be able to generalize on unseen test cases, and these are also pretty well. The true models are basically the models adopted by Kurukshetra 2022, and we also obtained, these models were the source of the search space, and they obtained decent results here as well. So the train set mean squared error was 0.00160, and test set mean squared error was 0.00217. When I convert this to the S-wave velocity, it corresponds to around, I think it was 10 meters per second in the test set. So this is a reasonable error. And when we trained this model on the noisy dispersion curves, the fits were slightly off and the mean squared error is approximately doubled. So this would correspond to an error of around 17 meters per second when you convert it into the velocity scale. So with these decent results that we had to present, this was the first step in automating the whole process of inverting for the S-wave velocity profiles. And with that, I would like to conclude my presentation. So again, I would like to bring out the key features of DispersioNET. First of all, it is agnostic to the number of layers of strata. It is robust to noise and dispersion curves as the error didn't significantly increase. And the we had a single architecture which could perform well for the cases which had increasing velocity layers, hidden low velocity layers, as well as high velocity layers. And the architecture is very light, and in the process of automation, when we have to deploy this in real world scenarios, this lightness of the architecture, which corresponds to the less number of parameters, will play a crucial role. So in the future work, I plan to work on uncertainty quantification to know how confident our deep learning model is when it predicts, and also perform the inversion of 2D profiles, as well as apply it on some field data. And with that, I would like to end my presentation. Thank you so much.
Is going to be DC Naskar and OP Misra. So DP Naskar is going to be.
Very good afternoon to respected chairs and geoscience community in the audience. I am DC Naskar, retired Director Geophysics from Geological Survey of India, and I have been retired on 21st January. And presently I am working in NCS, National Center for Psychology, New Delhi. So this work just carried out on behalf of Geological Survey of India when I was in there. And on behalf of NCS, that is the left logo, I am presenting here. The title of the work is just Geological Resistivity Survey and Case Studies in India. This is OP Misra is the Director NCS and Advisor Minister of Earth Sciences. At that time, when he was in GSI, the work was conducted and he was associated with this work. And first, I want to show the geological resistivity survey in Normudas ligament, because it is very much well known that Normudas ligament is a repeat component. With the help of the resistivity survey, electrical resistivity survey, both in Islamabad as well as dipole equatorial resistivity survey, just I want to find out the faulting or some lifting in the shallow subsurface structures. That is the objective, and also some dispositions of the various rock formations in that area. Because in Normudas ligament, the stratigraphic sequence just Quaternary, then followed by Cretaceous, Mesozoic, and then Proterozoic. That means Indian, These are Mahakoshal and then Archean basement. That is the stratigraphic scenario in central India, Narmada Sound linearity. And formula is associated with the Schlumberger resistivity sounding, this one, pi L square by 12L, and equatorial dipole resistivity sounding. This formula is associated with these two methods. And this is the location map. That is the south portion is the Borgaon, that means where the swarm activities, Pandhana, occurred in 1997. And 1997 geophysical earthquake as well as 1998 at Pandhana, swarm activities occurred. So this work at that time was carried out. And transit was just 150 km from Borgaon to Ujjain. And here just 15 equatorial dipole sounding has been carried out along with Schlumberger as well as magnetometric survey in that across the Normothesan linearity. Just for identification, I have showed the location map. And this is the Schlumberger as well as bilateral representative sounding curve from Borgaon, and that is from Dharampuri. And just Normothesan lineament is near about Barwa, in between Omkareshwar and Barwa. This is the position. And some shifting of the equatorial dipole sounding is very much prominent at Barwa because this is the presence of Normothesan lineament here in that area. And Schlumberger
is not getting displayed, so you can use pointer.
Okay. And Schlumberger resistivity sounding just Schlumberger resistivity some first portion, that is every by 1 km. Schlumberger sounding carried out, and then afterwards equatorial dipole sounding with R bar 10 to 12 km. And bidirectional equatorial sounding averaged out, and it is added to Schlumberger equation because there is a procedure, Bhattacharya Patra, for card matching technique. We have interpreted the resistivity sounding data, and these are the sounding. And this is one inversion here, some characteristic sounding curves that just I have shown here. And just to say, each and every sounding, it starts from decanter and followed by sediments, some gondwana as well as then proterozoic and then basement. Since in the overlapping sediment as well as the decanter, both are overlapping resistivity, so it is very much difficult to distinguish in between them. Apart from that, just high resistivity towards south of Narmada river occurs as 700 to 800 meter, and whereas the south of Narmada river, that means here the resistivity, high resistivity occurs at a greater depth. So, but at the Narmada river, the high resistivity encountered at a depth of 60 meter, approximately 60 meters. So, this steep gradient of the basement could possibly be attributed to the fault zone, and Narmada river goes right over the fault zone. And these are the findings of the resistivity sounding data. Apart from this, and each and individual formation is clearly picked up in the resistivity sounding results. And this is the collinear dipole profiling system. This also conducted because for findings of the zoning and lateral discontinuities. So there are a couple of faults are identified, and that is recorded for both the profiles, and with dipole separation 500 meter. With the 10 kilowatt generator and RDC10 receiver, I have collected the data up to 500 microvolt, and that is signal is very much dominant at that time. And these whole towers are within the decanter, and within the decanter conductive pockets are also picked up with lowering the resistivity. This may be the intercurrent bar or lamella events which are present in the Narmada river region. So from this collinear dipole profiling, some lateral discontinuity very much identified both the profiles, these and these. And conclusions, both resistivity and profiling is very much effective tool for delineating the subsurface structures as well as the lithology and structures below the decanter, because it's a very much challenging job for life below decanter. With the help of this resistivity survey, we have identified it, and along with gravity and magnetic survey as well as magnetic survey for intuition, we have conducted simultaneously with that. But since I have only I have shown here the resistivity only. And this is the electrical survey over Sikkim, Darjeeling, Himalaya. Objective is like that. Because in Sikkim, Darjeeling, Himalaya, it's a challenging job to find out the thickness of the symbolic sediments, tertiary symbolic sediments. So we have used the 10 kW generator with 10 to 12 ampere current and RDC10 receiver to pick up the signal up to 500 to 600 microvolt. And our bar is 10 kilometers. 10 kilometers, that means transmitting and receiving dipoles distance, and AV dipoles which Schlumberger's sounding up to 3 kilometers, that means 6 kilometers Schlumberger sounding in order to find out the lateral discontinuities in the relay. And this azimuthal sounding, I have used this formula. And this is the locations of the sounding locations, both in East 31, that is Punya to Sheva, and another one, NH 34 from Raiganj, Kishanganj, Korondiki to Sheva. This long transit we have covered with resistivity sounding, gravity, magnetic survey also. So with the resistivity survey, just I will give the results only for resistivity and some gravity survey also. And this is the sounding curves, resistivity sounding curves. Both the sounding curves, in the sounding curves, Schlumberger as well as azimuthal dipole level sounding are just added, and dipole sounding curves are also averaged in order to find out the basement, keeping up the basement. Because dipole sounding is very much effective for finding out the deep of the basement. And these are the locations, different locations of the sounding curves. And these are the sounding curves only for Schlumberger sounding, because inaccessible, due to inaccessibility, azimuthal dipole sounding it may not be possible at that time. And I have conducted only Schlumberger sounding with AV by 3 kilometers. Finding good results has been obtained, and only one prominent feature in the sounding number 14, that is high resistivity up to high resistivity in the surface 1100 meter is picked up in the afterwards lowering of the resistivity curve is finding. This may be interpreted as a symbolic sediment in the area, because it is very much prominent in the foothill of the Sikkim, Darjeeling, Himalaya. Symbolic sediment is also present. And this is the civil sections of the resistivity sounding curves. And just to see, there are F1, F2, F3, these parts are depicted in the figure, and this arrow just show the shifting of the basement, and upper zone is represented by the high resistivity. This high resistivity zone is very much important for oil and gas environment, because symbolic sediment is present in that area, and it is characterized by the resistivity up to 10 to 40 meter. So this region is very much prominent for economic point of view, and good result has been obtained in the resistivity sounding area. And this is the gravity contour map, and it is started from 69 milligram to minus 138 milligram, minus 69 to minus 130. So decrease in resistivity gravity from southwest to northeast, northeast direction, and some stabilized structure or hump-like structure is often there, which is very much important. That is also corroborated with the resistivity sounding result in that area, which is very much prominent. And the next one. And conclusion, due to the high conductivity of the overlying sediments, so penetrations of the resistivity sounding is not possible at greater depth, and almost the pseudo depth section resistivity indicated 4 parts, which may be indicative of the thrusting of the symbolic sediments. This may be basement thrust over the symbolic sediments. So it is very much prominent stratigraphic scenario in the Sequestration Himalaya also.
Can you please
May I
show
continue?
the island, Sagar Island also, can you show? You have not shown that, Sagar Island.
Which one?
Sagar Island.
Yeah, Sagar Island. Sagar Island, that is a very challenging one because in that area, fresh water, thickness of the fresh water and bedrock depth, it is very much, it is inefficient in any geophysical method to characterize the bedrock depth. But I have
Could you
conducted.
maybe just show one key thing?
Conclusion.
Time is up.
Okay. In the Sagar Island, just 4 or 5 subsurface structures have been delineated. Topsoil alluvium, which is followed by the clay saturated with saline water, and then it is followed by the brackish water, clay saturated with clear water, and fresh water bearing zone has been delineated at a depth of 250 to 300 meter. Afterwards, bedrock is delineated. Bedrock is delineated with the mangrove generic sargars.
What is bedrock there?
Yeah, it is not a bedrock in the Sagar Island because it is object in empty surface. Because in
time is
restriction-
up, so we are going to have question
Okay,
answer session.
I have to finish because there are so many case studies. I have to finish here on the Sagar Island. itself.
You are done. Fine.
Yeah.
You can stay here, and the remaining presenters who presented the paper to please come on the stage so that if there are some questions or comments, we can have.
Yeah.
From that, how can we infer all these faults and everything?
Because sir, in RMD officer just have plotted the resistivity data.
You have not converted into model, actual
Yeah.
resistivity model, you have not converted.
No, it is not converted. Just I plotted the apparent resistivity along the axis and
I know that.
along the body.
Then how can you infer all these tectonics from that pseudo section?
Because the tectonic, that is civilization is mainly responsible for the lateral discontinuity or lateral, but in that figure it is actually deep resistivity sounding up to urban since it is 10 to 12 kilometer, so we can give some idea regarding tectonic event also because the transit was 120 kilometer.
And second thing is that in the Sagar Island, you are told about the basement, bedrock.
Yeah.
What is bedrock there?
Bedrocks are sandstone, maybe sandstone because
At what depth? At what depth?
at what depth means 320 to 350.
No, it's not like that. It is not like sandstone is not there in 300 meters depth.
Actually, sir,
Thickness of alluvium is more than 800 meters.
yeah, but in resistivity survey, fresh water contamination zone is obtained at 250 to 300 meters. And
Resistivity-
afterwards, high resistivity is obtained with the magnetic survey.
But that doesn't mean that you have got bedrock. Sandstone.
But sir, it is better in high resistivity,
Please,
so I
please.
can't define.
There are n number of ONGC boreholes in the area.
Yes, well, it is there because we
Because I have studied all the boreholes of that area in detail. Nowhere sandstone is there at 300 meters.
There is a litholog is corroborated with our resistivity sounding data. I have followed the litholog data also, PhD
So
litholog
we-
data.
You can discuss
Okay,
later
okay.
on, no problem, because you have extensively
Because
been working
in the
and
Bengal
lot of
plain
experience
alluvial
of-
thickness.
I am really amazed with the excellent presentation by these youngsters,
Yes,
and they have done excellent job. Really, it is
Yes.
overall. So
Very
please
good.
do it. And regarding this AI applications, please use other methods also. For example, random forest you have used. You can use SVM. You can use LSTM. Please use all those techniques and then compare. Okay, that's all. Thank you.
thank you. So, any more questions? I'm sure there should be more questions from the audience. As there have been very good topics here presented by these youngsters who are working in machine learning applications.
Yeah, about the Narmada zone measurement profile what you have shown.
Which one?
Narmada,
None of the sun, dipole level profile.
1971 India
and GSI has performed a K1 magnetic survey and picked up a huge magnetic anomaly in an area called Gatavara.
Okay, I have also conducted magnetic survey there. Across the Narmada, there are 4 profiles, each and every length 400 kilometers. Myself conducted in that area.
But the depth what you have shown is only 1 kilometer.
Yes, because magnetic is very much, in that area, magnetic is very much fluctuating since the control is present there. So, fluctuating magnetic nature is observed in the second.
But there is a Canadian company which has done the borehole more than a kilometer. Maybe you are aware of that?
Which one? More than?
A kilometer.
1 kilometer?
Yeah.
Yeah, because deconstruct thickness is 500 to 1.2 kilometers.
But they are stuck with the BIF down there.
Yes, sir.
Yeah.
Yeah. That is
So, can you throw any light on the magnetic anomaly there? What could be the reason for that?
because I have magnetic model, 2D magnetic model is obtained in that area and map to the base with the map to the base. So thickness just boundary of the trap as well as mesodry is.
What could be the reason for that magnetic anomaly? I mean,
Yeah.
what could be the reason for that huge magnetic anomaly?
Magnetic anomaly, that is dye-like structures within decanter and some intrusives within Gondwana. Because Gondwana sediments is very much prominent with basic intrusives. So it will give the high magnetic signature.
So
In that area.
Gondwana is extending from all along from.
Gondwana is south of the
So do you
Narmada
expect
river.
all the magnetic anomaly?
Throughout south of the Narmada river from Betul to up to Nagpur and Wardha Valley also. That is long stretch is there because 1500 kilometers is the Narmada Sunita mountain and south of the Narmada river during the Mesosolic period, Deccan and Mesozoic 65 million years, this event has been occurred.
I think this is a fantastic discussion to take further during lunch. I think you gentlemen have still a long time to talk about this topic. Let's try to get some questions to the other talks. Dr. Ran.
I have a question. First of all, it was a wonderful session. I have a question for Mr. Rohan Sharma. And first of all, congratulations, you are doing a great job. And I really hope you take it forward very seriously because this will solve a lot of problems in the inversion of MESW. Now, when we talk about the non-uniqueness in the inversion of MESW, we look at the models where there is a low velocity layer sandwiched in the high velocity, between the high velocity layers.
Yes, this is a typical.
Where a typical scenario where non-uniqueness really comes to the front, right? Whatever initial model you give, it tries to obviously close it near that particular model. So with your AI network, I was looking at all the models, machine learning models which you have created. Most of the models still are having the linear progression of velocity. Okay, one model was having a little lower velocity, but there your prediction again went to the same linear progression, right? It did not come back to the low velocity. So are you trying to test more data on these kind of models in future?
Yeah, so and one approach that I'm thinking of currently is that I'm actually thinking that there is a bit of information loss when we do the curve picking and dispersion curves. So I was thinking of feeding the dispersion images, which are the wave field transform of this short gap is directly to this. I believe that there could be a bit of improvement in the accuracy because of that. Because the HVL and MVL information as per theory is contained in the higher modes. So I believe that in the picking of higher modes, there might be some discrepancies which might cause this issue. So one thing is by gathering more information at the limited amount of data itself, they could solve this. Another approach is that we could try even complex, machine learning models like vision transformers. So I actually had a run after I presented this after I submitted this paper to the AG conference. So vision transformers were clearly outperforming the CNN model, and I would probably go on to present it in another publication with uncertainty quantification so that we could know how confident the AI model is with its predictions. And I will also extend this work to 2D and probably 3D one day, the time of perfect sense.
Wonderful, Rohan. And please keep it up and please continue this work. And do not wait for the next conference. Keep in touch. We also have lots and lots of field data which we keep generating. We would love to collaborate with you in this.
That is something I must do.
Yeah, sure, please. Let's
Thank you so much.
Keep working on this. Thank you very much. Yeah.
In my literature review, I encountered a lot of people who have come across a lot of optimization techniques that are popularly known, like PSO, GW, and all of that. So the that is what I was trying to address. There are also literature in deep learning as well, but the local optimization algorithms suffer from this, local.
You mentioned some algorithm. I'm not getting that name. You also on your paper one of PPT.
Okay.
There is some optimization algorithm you mentioned for using machine learning.
So we use CNNs.
Yeah. So what is the uniqueness of it?
So CNNs, basically when the original deep learning model that was in literature was called artificial neural network. So CNNs are basically a way to reduce the number of parameters that are used to learn the features. So yeah, it keeps your model light. Basically, you don't need a lot of computations with the help of CNNs.
So still it is converging in linear as well, linear convergence. So it is not finding the global minima or maxima, the CNN.
So if you are acquainted well with deep learning, then the problem of local minima it does exist, yes, but the local minimas are all sort of like very close to the global minima, and therefore this problem is kind of solved. Not very.
Okay.
Thank you so much for that.
I didn't know, not audible, but so we are really happy to have such a senior person in this very session. Thank you, and Asmita Ray, Das, both are from academia, and Mr. Sam. So thank you very much. Thank you.
I would now request our chairperson, Dr. Andy, and Professor Satybir Teotia to please come up on stage to facilitate their offers.
Oh, it's okay.
Ms. Asmita Ray. Mr. Rohan Sharma.
Wonderful. Keep it up.
And Dr. D.C. Naskar.
We all will be using our hands to eat food. Let's put them up together, multiply them.
I would now request Dr. T.C. Chandra to please come up on stage to facilitate our chairperson. Thank you so much, everyone.
Excellent job. Yes, keep it up.
Pavni, you need a group photograph also? Yeah.
Now, we already have our posters installed at the back of this hall. Please visit them. And we'll be having an early lunch today. So it's 12:46 and we'll have our lunch in the exhibition area and we'll meet exactly after an hour at 1 o'clock.
I am still there. I am still there. They are telling that they will throw out my distance. See the way somebody treats me.